For the class, let's first take a brief review of what we have learned in the last two classes. Okay, here are some key terms. First, position vector is defined as the relative position um, expressed with time t, and we have motion function and displacement or path. Then we learned how to solve the problems with the equations. Okay, here we have solved this problem. And then we learned about the velocity and the speed. And then we distinguished in which circumstance the velocity equals the speed. And then we come to the definition of acceleration. Acceleration is the average of the addition vector of velocity v, and it can be expressed as the first derivative of velocity and the second derivative of the position vector. And we have two kinds of problems in kinematics. The first one, as we described, is the derivative, and the second kind is integration. And we deduced the following equations using the calculus-based physics. Okay. And we have solved this problem. Okay. This is the end of our last class. So here we come to the example 5. A particle starts from the origin at t equals 0 with an initial velocity of 6 meters per second along the positive x-axis. If the acceleration is 2 and 6x squared, determine the velocity of the particle at the moment it reaches x equals 2 meters. Okay, for this problem, it seems a little different from what we have learned. The acceleration is a expression, is a variable, and the acceleration changes with x, right? So in order to determine the velocity of the particle at the moment it reaches x, we have to find what we have to find the basic ideas of how how the particle moves. Okay, let's see the solution. Because the acceleration equals 2 and 6x squared, we know that the acceleration is the second derivative of x. And when t equals 0, x0 equals 0, and v0 equals 6. And a is the first derivative of velocity dv dt. And we can also rewrite dv dt as dv dx dt. And dx dt equals v. So we have this function 2 and. Okay, here it equals what? 2 and 6x squared. So if we put this term here, dx here, we have this function. The integration from x0 to x a dx equals the integration of v from v0 to v. And we have this function v squared equals 36 and 4 multiply x and x cubed. So here we can see when x equals 2 meters, v equals 8.72 meters per second. So this is calculus-based physics. In order to solve this problem, you have to use the integration. Example 6. The motion of an object falling from rest in a resisting medium is described by the equation dv dt equals a minus bv, where a and b are constants. In terms of a and b, find a. Find the initial acceleration. B. Find the velocity at which the acceleration becomes zero. Or we also call it the terminal velocity. C. What is the velocity at any given t? Okay, in order to solve this problem, we have to solve it one by one. Problem A, find the initial acceleration. Here, we know that the acceleration is expressed as dv dt. So, it moves in a straight line motion, and a equals dv dt. equals A minus BV. And it moves from rest, which means V0 equals 0. So we can see the initial acceleration A0 equals A. Okay, then problem B. Find the velocity at which the acceleration becomes 0. In order to find the velocity at which the acceleration becomes 0, we can say when A equals 0, when A equals 0, dv dt equals 0. When A equals 0, dv dt equals 0. So A minus BV equals 0. So V equals A over B, right? Here, we didn't write it here. V equals A over B. Okay, problem C. What is the velocity at any given t? When dv of dt equals A minus bv, we can write it here. We can put dv in one side and dt on the other side. And then we can put every term containing v on one side and every term containing t on the other side. Then we can write it here. V equals A over B multiply 1. Okay, we can give the velocity at any given t with this expression. Okay, then example 7. The position of a particle moving in the xy plane is given by r equals I are cosine omega t, and J are sine omega t. Problem A show that this represents circular motion of radius r centered at the origin. And problem B, determine the velocity and acceleration vectors and functions of time. And problem C, determine the speed and magnitude of the acceleration. D, show that A equals v squared over r. E, show that the acceleration vector always points towards the center of the circle. Okay, for this problem is the fundamental of the circular motion. So I want you to try to solve it by yourself um, in 3 minutes. I will give you 3 minutes to trying to solve it, and then after 3 minutes, I will show you uh, how to do it, how to deduce all the problems. Okay, for problem A, show that this represents circular motion. This is very important. This is very easy to solve. In order to show that this is circular motion, you just need to prove that the radius that at any given point on the on this motion, uh, it has a radius r. Uh, it has a distance of r from the origin. So, in order to calculate the distance between that point and the origin, you need to do what? You need to calculate what? The magnitude of this vector r, right? So the magnitude of this vector r equals root x squared and y squared. So x squared and y squared equals r squared, and the magnitude of r equals big R. And problem B, determine the velocity and acceleration vectors as function of time. Okay, B to E are solved. Are solved altogether. We can see them all together. For problem B, determine the velocity and acceleration as function of time. And problem C, the speed and magnitude of the acceleration. D, show that the acceleration equals v squared over r. And E, the acceleration vector always points towards the center of the circle. Okay, determine the velocity and acceleration. We know that v equals this term dr dt, and by doing the derivative of r, we know that the first term on the x-axis equals minus r omega sine omega t, and the second term on the y-axis equals r omega cosine omega t. And we know that the magnitude of the velocity equals omega r, and the acceleration equals dv dt. And for at any given point, the first term equals minus r omega squared cosine omega t, and the second term equals minus r omega squared sine omega t. And we can also get the magnitude of acceleration. It equals omega squared r. And we know that omega equals v over r squared, and it equals v squared over r. And problem D is solved. And for this problem, we know that V, here V equals what? Minus R omega, R sine omega t. And we have R equals what? R equals this term. And we can see there is some relationship between R, the projection vector, and the acceleration. It seems they are linear, right? The acceleration, the direction of acceleration is always the opposite direction of projection vector R. So problem E is solved. The acceleration vector always points towards the center of the circle, and the projection vector R always points towards the outside of the circle. Okay, here we come to example 8. The position of a particle is given by r equals ti and t squared minus 2tj. Problem A. Problem 1. So determine the particle's velocity and acceleration and t equals 2s. This is quite simple. When t equals 2, we have this position vector, and by doing the derivative of position vector, we have the particle's velocity dr dt. And then we also have the acceleration dv dt. And by putting t equals 2 into the two equations, we can get the magnitude of the two terms. Problem 2. Okay, then I want you to solve the remaining problems by yourself. If you have got the answer, you can write down. You can text your answer on the chat box. And I really want to know how many students can get the right answers. Let me see. I think 5 minutes is enough for you to solve it. Okay, let's see problem 2. Okay, for problem 1, we have got some right ideas. V equals I and 2j, A equals 2j, right? And problem 2, what was the average velocity of the particle between t equals 1 and t equals 2? In order to calculate the average velocity, we need to first write down the position vector r, and when r equals when t equals 2, we have the function r equals 2i and 2j, right? And when r equals 1, we have 1i and minus j. And by doing the by um, using this equation, r when t equals 2 minus r when t equals 1 over delta t, we have the average velocity I and j meters per second. Anyone right? Okay, here we have two students were right in this answer. Okay, I think the two students have got to know how to do the calculations. And problem 3. What is the shape of the path of the particle? Okay, when we have r, the position vector r, and the two terms, we have two components, x and y. They can express like this. And by calculating the trajectory function, we know that x equals t, so we can put x here, y equals x squared minus 2x, and we can draw it on this plot. This is the trajectory of this motion. Okay, problem 4. What is the velocity perpendicular to what is the shape of the what is the velocity perpendicular to when is the velocity perpendicular to acceleration? And 5, what is the distance for t equals 0 to t equals 1? Okay, in order to find the time when v is perpendicular to a, we need to first write down the two terms, the vector form of the two terms. When they are perpendicular, they cross a equals 0. So 2, here we have this term, 2 multiplied 2t minus 2 equals 0. So t equals 1. And for problem 5, in order to find the distance, we need to first write down this. V equals ds over dt, and it equals this. Now we can calculate it. Okay, next problem. Let's take 10 minutes break, and then we 10 minutes break, and after 10 minutes we will solve this problem.